Good day, class. Today we will be continuing our study of kinematics and mechanics with chapter 10 of the textbook on momentum. So please turn your textbooks to page 189 and we'll start from there. Now, many of you will know linear momentum, the concept of linear momentum from physics. Today we will be exploring linear momentum in the mathematical sense. So as you already know, the linear momentum of an object with mass traveling at some velocity with the vector v in meters per second can be defined as momentum is the mass multiplied by velocity. In this case, we'll be working with the unit of kilogram per meter seconds or Newton seconds. Okay. Now, momentum is proportional to its velocity. Mass is a scalar and velocity is a vector. It therefore will follow that momentum is a vector quantity, okay, from scalar multiplication. Now, where we use momentum mostly is in terms of collisions. Eventually, we will get to the law of conservation of momentum, which just simply states that momentum before a collision and momentum after a collision should equal each other for the entire system, where one part might be able to change. For example, up here we have a truck colliding with a car. Afterwards, the truck might have less momentum than it originally had, but the entire system's momentum will be the same. Let me switch to my board here and we can discuss that a little bit. Okay, now we've discussed as momentum, we have discussed momentum as the product of mass and velocity. Okay. Mathematically, that can be written as mv. Okay. The principle of conservation of momentum states that, just a note here, momentum can also be written as P, which you should be used to from physics. So, our P initially should equal our P finally. Okay, so what does that mean? Now, we can write this as a sum of all of our objects within the state. So our summation, mass of object 1, the velocity of object 1, these are all vectors. Okay, so rather the mass of all of our objects initially should equal the sum of the masses and their respective velocities finally. Okay. So, for the textbook example over here, what we have is a truck with mass 2,500 kilograms or 2.5 tons colliding with a car of 1,000 kilograms or 1 ton, and they are moving at different speeds. So, let us simplify this example. In our textbook here, I will be showing the truck as a blue sphere and our car as a red one. We will define right as positive. We know the mass of the truck is 2,500 kilograms and its velocity is to the right, traveling at 10 meters per second. Furthermore, we know the mass of the car being 1 ton, 1,000 kilograms, and its velocity being 20 meters per second to the left. In other terms, make it smaller. This is my initial case. Okay, so here my truck is traveling to the right and my car is traveling to the left. Now, they will collide. Okay, in that case, we're not exactly sure what will happen when they do collide, but my intuition tells me that both of these objects will be traveling to the right. So, let's have a look for the final case. So, to start that, let's use our principle of conservation. The sum of my momentum before should equal the sum of my momentum after. Therefore, we can say mass of the truck, velocity of the truck, plus mass of the car multiplied by the velocity of the car. Now, we need to include our signs as we are working with vector units. So let's do that. We have 2,500 multiplied by 10. And over here we have 1,000 multiplied by -20. Okay, this becomes 25,000 subtract 20,000. And we are left with a net momentum of 5,000 Newton per second, or kilogram per meter per second. Okay, so this tells us the entire system has 5,000 newtons per second in excess to the right. Therefore, we should also know that our final momentum should equal 5,000 kilogram meter per second to the right. Okay, now you do not have to indicate to the right, since we have denoted right as positive, we can just leave it there. Okay, if we make the assumption that our two objects collide with each other and move together, that means that our final momentum will be defined as the combined mass of my car and my truck and the combined velocity thereof. Now, to solve for that final velocity for this little vector component there, all we need to do is to fill in what we know. We know we have a momentum, a net momentum of 5,000 kilogram meter per second to the right. We know our combined mass is just 2.5 tons plus 8 ton, which would be 3,500 kilograms, and we are only looking for V. Solving for V, we find that value to be 1.43 meters per second to the right, which we indicate with a positive value. So, these two vehicles colliding will experience some force when they do strike each other. That force we will call, or we will consider in terms of impulse. Your textbook makes a little note of the impulse here in this note, stating that the effect of the constant force F acting for some time t is a change in momentum of each vehicle of ft, and this is described as the impulse acting on it. The impulse acts to the right on the car and to the left on the van. Okay, so when they do strike each other, they experience some force over some time, and that will cause each object to change their momentum. The car loses all of its velocity to the left and instead starts moving to the right. The truck itself has to slow all that momentum down, and it will lose some force and some energy to deformation, However, the entire system's momentum remains unchanged, and we find that the combined mass of these two vehicles will be moving to the right at 1.43 meters per second. This illustrates the law of conservation of momentum. In words, it simply states that when there are no external influence on a system, think friction, think energy losses to deformation, or so on and so forth, heat loss, energy loss, sound loss, whatever the case may be, the total momentum is constant. And this will also apply with the vector nature to the magnitude in any direction. So therefore, the total momentum before a collision should equal that after the collision. Okay, it's important to note that while momentum is conserved, mechanical energy is not. Some of the work done by these forces will be converted to heat and sound. In physics, we discuss this as elastic and inelastic collisions. In this case, if there is some deformation, if there's sound loss, if there's heat loss, it will be inelastic, since the kinetic energy before will not equal the kinetic energy afterwards. Okay, moving on to the next page. This is example 10.1. Example 10.1 shows us, basically just what we did just now. We have the two vehicles here, right is defined as positive, and they ask us to draw the situation before and after. We should find the final velocity of the car, and finally we should find the kinetic energy lost. Okay, so to give us a little helpful hint, note here they say when you are solving for an impact problem, always draw before and after diagrams. This is very, very good advice, especially for your exams. It will not necessarily waste your time, but it is very important to do. There is one caveat though. In our example, we assumed that both vehicles will be traveling together. This example states that the van will come to rest. Okay, so we must alter our assumptions a little bit for this one. Now, to save us a little bit of time, I'm going to use the textbook's drawing here. So the vehicles are modeled here in 10.3. We have our 2.5 ton truck moving to the right, our ton vehicle moving to the left at 20 meters per second, and the van at 10 meters. Afterwards, we have some V for the car moving backwards, and we have 0 velocity for the truck. Okay, back on the board, let us use, so part 1 has been done for us, I will do part 2 for us. Okay, we will use the momentum after should equal the momentum before. Originally, we said that our momentum before was 5,000 kilogram meter per second. Okay, and that should equal the momentum after, which will be given to us by the sum of the two momentums. We have our truck, the mass of the truck, multiplied by the velocity of the truck, and the mass of the car, multiplied by the velocity of the car. Now, we know that the velocity of the truck, this guy over here, is 0 in the final case. Therefore, we can simplify our equation by taking that as 0. Then we are only left with the momentum of the car, as if there's no velocity, there is no momentum. Any product that you multiply where there is a 0 in, any 0 product will stay 0. Okay, so all we have to do is calculate the momentum of the car. That will be 1,000 kilogram multiplied by some V, and now we have 5,000 kilogram meters per second is 1,000 multiplied by V. So to solve, we can divide 1,000 on both sides, solving for V to be 5 meters per second to the right. Okay, so we saw now in our previous example, if both vehicles were traveling together, if there was some deformation between them, causing them to get stuck, then both of them would be traveling at 1.43 meters per second, whereas if the truck came to an entire halt, all of its momentum was transferred into the car. It not only cancelled out the original 20 meters per second that the car was traveling, but it rebounded it at 5 meters per second. Okay, for the third part, we need to calculate the kinetic energy of the system. So we need to compare the kinetic energy before and the kinetic energy after. We'll start with the initial case. The initial kinetic energy of the entire system would be the sum of all the kinetic energy of the parts present, which in this case will be equal to the mass of the truck, the velocity of the truck squared, now note that this is a scalar, plus the mass of the car and the velocity of the car squared as well. Initially, we will do the exact same thing for the final case. Okay, so let's fill in our values. We have 2,500 kilograms for the truck traveling at 10 meters per second squared, and the car of 1,000 kilograms multiplied by 20 meters per second squared. We will get 250,000 joules for the truck and 400,000 joules for the car, for a total sum of 650,000 joules, or a little bit simpler, 650 kilojoules. Alright, let's look at the final case. So in our final case, our kinetic energy again is the sum of the kinetic energies of the system. So that will be the mass of the truck, the velocity of the truck, plus the mass of the car, velocity of the car. These are squared. Oh, I seem to have made a little mistake here. This should be a half in both cases. So simply put, we can factorize that out, and we can simply take it as half of 650,000, which is 325 kilojoules, if I'm not mistaken. Okay, on this side we shouldn't forget our halves there, okay, which we can factorize out again, making our life a little bit simpler. Again, this is not traveling at any speed, or any velocity, so we can simplify that to 0, left with finally a half of 1,000 kilograms traveling at 5 meters per second squared, which will be 25,000. 5 squared is 25 times 1,000, 25,000, 12,500 joules, simplified as 12.5 kilojoules. Okay, and now we can see clearly our kinetic energy finally does not equal our kinetic energy initially. In physics, you would call this inelastic. As far as I can tell, that information is not important for the mathematics. Okay, moving on. One final thing, we must just also find the difference. They wanted the change in kinetic energy, which in this case is 325 minus 12.5, or more correctly, the final minus the initial, which in this case is negative 312,500 joules. Okay, lost. Okay, moving on to the next example. So, in example 10.2, there is a new experiment with lorry bumpers. They've arranged for some test where a lorry and a car with masses 1 ton for the car and 3.5 tons for the lorry to travel towards each other both with 9 meters per second of speed. After colliding, both vehicles move together. What will be their combined velocity? Looking at this here, we can see they have drawn the situation for us here. We have our car traveling at 9 meters per second to the right, and our truck moving to the left, with right being defined as positive. And here you can see that first example I did with you guys where the two travel together. Okay, now they are using a little bit of a different way than we did earlier. They are going to kind of do it in a table method, which is fine to do. They are going to define the momentum of the car, Newton seconds, as 9,000, just simply being 1,000 multiplied by 9. The lorry being 3,500 multiplied by -9, since it's traveling to the left. And that together gives me -31,500. Our total momentum, therefore, is -22,500, or 22,500 Newton seconds to the left. After the collision, we will assume that they move together, just as we did in our earliest example. And therefore, we will consider their combined mass. 3,500 plus 1,000 will give me 4,500. 4,500 kilogram traveling at v, the final velocity, should equal the original initial momentum, which was 22,500 to the left, and therefore if you solve for v, you find that the car and the lorry will move at 5 meters per second to the left. Nothing too fancy there, nothing that you cannot do or that you haven't seen before. Okay, let us look at example 10.3. A child with a mass of 30 kilograms is running through a supermarket to the right at 4 meters per second. He then leaps onto a stationary shopping trolley with mass 15 kilograms. We should then find the speed of the child and the trolley together, assuming that the trolley is free to move easily. Now this is exactly what we've just done. Nothing funny to it, except that now we have one stationary before the collision, and they are traveling together after the collision. So if we take the direction of the child's velocity as positive, we'll take the starting velocity as positive. His total momentum is going to be his mass, 30 kilograms multiplied by 4, plus the product of the trolley's mass and its velocity, which in this case again simplifies to 0. And we find that the total momentum before collision is 120 Newton seconds. After the impact, we are now working with the case of their combined mass. 30 kilograms plus 15 kilograms will give me a total of 45, traveling at v. 45 v should equal 120, and then again applying algebra to solve for v, we find that v is 2 2/3 meters per second. Nothing funny, nothing you've never seen before, no funny math, simple and easy to solve. From there on, we can move to example 10.4. Here in this case, we have two smooth spheres, sphere A with 2 kilograms of mass traveling to the right at 7 meters per second, which will eventually collide with object B, which is a 3 kilogram sphere traveling at 2 meters per second to the right. They move on a smooth horizontal plane in a straight line. Lovely. We should find the velocity of sphere A and the loss in kinetic energy of the system. Okay, so let us do that. Let's see, maybe we'll do this example here. This is example 10.4. Just to confirm, we have mass A moving to the right, about to collide with mass B moving to the left. And for simplicity and clarity, let's color them. Mass A, we said, had mass 2 kilograms, traveling at 7 meters per second to the left. Mass B, on the other hand, is heavier. It has 3 kilograms of mass, traveling at, in this case, negative 2 meters per second. Lovely. This is our before case. If we assume that they do not get lodged in each other, I think it would be good to assume that they will hit each other and rebound in the opposite directions. So let's consider that finally they will be traveling in opposite directions. Let's just see if there's any more information that they give us. Opposite after the collision, we find that sphere B moves to the right with speed 2 meters per second. Okay, so in this case it's moving with positive 2 meters per second because it's moving to the right. Take note that we have defined right as positive. Okay, so this case is easily enough to solve because all that we are looking for is V. Were it the case that we were not given the information that object B was traveling to the right, the only way we'd be able to solve is if we decreased our variables and we said that it is a combined object traveling in some direction, we do not know which, we'll assume it's to the right with velocity V. If we did that, then we could still solve, but if that was not the case, then we need at least one of the object's velocity to find. Okay, to simplify, I'd like to show you guys a way I like to solve for this. I like to say P initial should equal P final, and then to summarize the momentum on my initial side, which will be 2 multiplied by 7 summed with 3 multiplied by negative 2. That should equal 2 multiplied by V plus 3 multiplied by 2. Okay, and now you can solve in one step, which I would like to do. 2 multiplied by 7 gives me 14 minus 6. On this side we have 2V plus 6. We'll take that 6 over to become negative 12 on this side. 14 minus 12 gives me just 2 equals 2V. Simple enough, V equals 1. Let's just write that in the right way. V equals 1 meter per second. Okay, and with that we have solved for part 1. Moving back to our example, they want the loss in kinetic energy as well, so we can do that. Our kinetic energy, we can also do it like this. Delta EK is equals to EK in final minus EK initial, and this is again for the whole system. So our original momentum, let's look at each of the objects. If we want to, we can do it that way. So we can consider the kinetic energy of A and B separately. So this will be a half of my M. Let's say M of A. V final minus V initial, both of these squared. Okay. Subtracts, and we're adding to half mass of B, and then let's just give ourselves a little bit more space here. That should do it. Okay, the mass of object B, its velocity final minus its velocity initial. Okay, so all I've done now is I've used this equation. If you haven't seen me use it before, delta EK is just going to be half of M and then V final minus V initial squared. That square should be inside. Or another way that you could have seen it perhaps was to be half mv squared minus u squared. It's just a matter of convention. And what I've just done is we know that our kinetic energy of the system is the kinetic energy of A plus that of the kinetic energy of B. Okay, where this will be of A, the change in momentum of A, and the change of momentum in B. Now, this isn't necessarily that you have to use this. I just like to expose you to a few different ways of doing this. You are welcome to use a method that you are comfortable with. Now, we can simplify by taking out these halves, which I'd like to do, make my life a little bit easier. Make a little nice big bracket since we factorized that half out. For A, we know our mass is 2 kilograms. It's multiplied by, okay, and then also we know now V is equals to 1 meter per second. Okay, so our final velocity is 1 squared, nice and easy, and our initial velocity was 7 squared. Okay, and on this side we have the mass of B, which was 3. Its final velocity is 2, and its initial velocity was 2 as well. 2 squared minus 2 squared. Lovely. That simplifies. Since this becomes 0, this entire term will become 0, and all we have to worry about is the change in momentum of A. Now, 7 times 7 becomes, can't remember, give me a second. Okay, forgive the interruption. This becomes half of 2 times 1 minus 49. Okay, 1 minus 49 becomes negative 48. Negative 48 times 2 will give me 96. Negative 96, a half of negative 96 will just be, oh well, simple enough. A half times 2 becomes 1. And then our loss in joules becomes negative 48 joules of energy lost. Now I might have gotten this wrong. Let's confirm. And we were right. We got it correctly. Okay, now they're going to use a different way. Doesn't matter, it's the same thing at the end of the day. I'd just like to show you that there is more than one way to skin these cats. For part 2, they want the velocity of D. Okay, well, hold on, there's a little bit of more. So in this second case, they say that there's 2 objects. We have B, C, and D. So B traveling at 2 meters per second after the first collision, then strikes object C that was moving, and they coalesce to form a bigger object D. Okay, so this is a little bit differently, but it's nothing funny. It's nothing that we haven't seen before. I'm going to leave this as an exercise for the reader. Okay. There's a very important note here stating that a common mistake would be to try to use kinetic energy before equals kinetic energy after. This is not true, and this will only be true if it is elastic in an elastic collision. Do not make this mistake. Please make sure you use the conservation of linear momentum and not conservation of kinetic energy. There are different things, and kinetic energy is not always conserved. We will then move on to explosions. Okay, explosions. Now, explosions is nothing different than a collision, except we are now colliding energy with particles. But that doesn't matter, because what an explosion actually just is, especially if we're taking this example for example of a rifle being fired, it's just gas which has mass and velocity expanding, hitting something and transferring its momentum to that object. Now, luckily for you, you don't have to consider something that intense. We will just consider something like a gun firing, and then instead of taking the gas as our one object colliding with the bullets, we will take the recoil as the rifle as the effect of that gas, simplifying our solution. Okay, so For example 10.5, we have a rifle with 8 kilograms of mass used to fire a bullet with 80 grams of mass. This bullet leaves the gun at 200 meters per second, and then we should find the initial recoil speed of the rifle. Simple enough. We know before the explosion there is zero momentum. The gun's not moving, so the bullet and the rifle both have zero momentum. Therefore, we can also find that we need to just find our momentum afterwards and set that equal to zero. Therefore, the momentum of the bullet should equal the momentum of the gun. If that doesn't make sense, let me show you what I mean. Okay, so they are saying here that initially the velocity of the rifle is zero. Okay, so that means that the initial momentum, mass of the rifle and the bullet and its velocity should also equal zero. Okay, from conservation we know that the initial momentum is equal to the final momentum. Therefore, the final momentum should equal zero. Okay, our final momentum is defined as the mass of the bullet multiplied by the velocity of said bullet plus the mass of the rifle and the velocity of the rifle that we are solving for, which I will call V. This should equal zero. Therefore, it is easy to say, therefore it's rather nice to say that the mass and the velocity of the bullet should equal, but in an opposite direction, the mass and the velocity of the rifle. Okay, now we know what the mass of the bullet is. It was 80 grams, so 80 over 1,000 multiplied by the velocity of the bullet, which was 200 meters per second. And then we know that the mass of the rifle was equals to 8 kilograms times V. Simple enough. Now all we need to do is to solve. Let's do that and do this and do that. A little bit of primary school maths. And then we're going to divide by 8 as well, so we can do this and that. Simple enough. V is equals to negative 2 meters per second. Now if you don't know what I did there, please go revise your fractions. It was just a little mental calculation. I'm sure your calculator will show you the same. So if my bullet is traveling with 200 meters per second to the right, it means that my gun is moving at 2 meters per second to the left. And that is it, ladies and gentlemen. That is chapter 10. Momentum. As you can see here, there's not a lot. We're not doing a lot of impulse, and in fact I don't see any impulse questions. We don't do is it kinetic or not kinetic. So if you have done physics, this should be a walk in the park. If you've not done physics, I'm sure that you've noticed that there is nothing really tough in here. For homework, I'd like you guys to just work through these questions, specifically the questions where we are involving other things. For example, over here we are involving a little bit of friction, which is lovely. We are involving a little bit of modeling, which is always fun. So please try, especially these ones marked as M, question 7, question 12, and then 13, 14, and 15.